This is a story in two parts. We start with a film originally made in 3D in 2007, and it looks back on the years of planning and construction from a time when the rebuild was nearing completion. In the second part of the story, we look back on 13 successful years of the rebuild in service, starting with the Royal switch on in 2007. First, that film. This is the mansion at Bletchley Park in Buckinghamshire. At one time, it was the headquarters of the Government Code and Cipher School. Now it is the icon of World War II code breaking. During World War II, Bletchley Park was responsible for reading enemy messages of many different types. Certainly the largest volume of traffic handled was the tactical network messages of the Wehrmacht, the Heer, the Luftwaffe and the Kriegsmarine. These messages were all encrypted by the Germans using the notorious Enigma Machine and broken daily by the British using a machine called the bombe. This was the brainchild of Cambridge mathematician Alan Turing and Turing Welchman, and was built by a brilliant engineer, Harold Doc Keane, of the British Tabulating Machines Company in Letchworth. By 1945, more than 200 of these remarkable machines had been built, but at the end of the war most of them were dismantled. All had disappeared by the 1960s. In 1996, a retired engineer named John Harper decided to build a fully working replica of a bombe and started to put together a team. This grew to over 60 people and included ex-engineers and enthusiasts with home workshops in garages, garden sheds and so on. My name is Mike Hilliard. For 8 years it has been my privilege to be a member of John's project team, and I would like to share with you a little of what we've been doing. This slide shows a typical 3-wheel Enigma machine similar to the type used by the German Army and Air Force. It has a keyboard, and a key pressed with a letter from the plaintext message results in a lamp being lit in a lamp panel immediately behind the keyboard. This represents its ciphertext equivalent. Electrically, between the keyboard and lamps lie a number of levels of encryption. There is a patching panel at the front of the machine, and then behind the lamp panel are 3 wheels or rotors, each of which scrambles the letters in a different way. After passing through the rotors, the signal path encounters a reflector, which, whilst scrambling again, turns the path back through the rotors to the patch panel and finally to the lamp array. To compound all this, each time a key is pressed, the right-hand rotor turns one position, changing the scrambling algorithm. When wheel 1 has turned 26 positions, it moves wheel 2 one position as well, and this is continued with wheel 3, rather like a car's mileometer. There were 5 different wheels to choose from in setting up the machine, and the 3 chosen wheels could be placed in any position. To further complicate matters, the letter ring on the outside of each wheel could be set to any of 26 positions in relation to the wheel's scrambling core. In all, this machine had over 150 million setup possibilities. To be able to decrypt the messages, one had to know which 3 out of 5 wheels were used, where they were placed, their ring settings, their starting positions, and the patchboard settings. Helping the Bletchley Park codebreakers to find these was the bombe's job. There were thousands of these machines, and this is a reenactment of a typical German installation in the field. The Bletchley Park codebreakers concluded that a head-on attack on Enigma wasn't an option. As the settings were changed daily, to be of any use they had to be found in a part of one day, and with the technology available, it would have taken far too long to cycle through all the possibilities. Turing's attack exploited a weakness of the Enigma machine, the fact that it couldn't encrypt a letter as itself. A could be encrypted as B through Z, but not as A. It also exploited weaknesses in the German procedures, typically that their messages tended to be very formulaic and contained predictable phrases, for example, weather forecast and Heil Hitler. This enabled the suggestion of a relationship between a short piece of plain text and a part of the ciphertext, this referred to as a crib. The crib could be presented as a so-called menu, something that could be set up and examined on the bomb machine. This is a front view of our replica bomb, and to give you an idea of scale, it is 8 foot wide, 6 foot high and 2 foot deep. It weighs about a ton. As you can see, it has an array of small stub shafts on the front, each coming through a commutator which is an array of contact pads. Each shaft can be equipped with a drum, which is functionally equivalent to an Enigma wheel. The shafts are arranged in 3 banks. Each bank has 12 columns, each of 3 shafts, and each column of 3 is effectively a separate Enigma machine, giving the bomb a total of 36 Enigmas. A menu could be set up by connecting together these individual Enigmas in a particular way with cabling on the back of the machine. Here are the menu cables being put in place. For a typical menu, this jack panel would be completely covered in cables. This picture shows the bomb set up with its drums in place. You will note that there are 5 different drum colours, and these relate to the 5 different Enigma wheel types. Once the machine was set up, it could be set running through all the 26 x 26 x 26 possible combinations of drum positions. The top row rotated continuously, whilst the second row stepped 1 position for each revolution of the top row. Similarly, the bottom row stepped once when the middle row had completed a revolution. Running through all the possible positions would last about 13 minutes if no results were found, but the run could be interrupted and stopped at any position if the machine's electrical circuits detected that the requirements of the menu had been met. The black-faced drums on the right are the indicator drums. When a stop occurred, the letter next to the pointer was recorded for each of these 3 drums. Other information from the machine was also recorded, but I won't go into that here. After a stop, the results were transferred to the checking machine, this to test the validity of the stop and to extract further information. All the results were then passed to the mathematicians in Hut 6 for further refinement. This replica checking machine has also been built by John Harper's team. This is a British Type X encrypting machine modified to emulate an Enigma machine. The final step in the process, when the complete daily settings for the Enigma machine had been discovered, was to transfer those settings to this machine. Then all the messages of the day could be decoded on this machine by typing in the ciphertext. The machine typed out the plain text, hopefully in German, on paper tape. In this way, all the messages of the day could be read, until midnight, when the German settings were changed and the whole process had to start all over again. Moving back to the bomb, this rear view gives some idea of the technology involved. You can see the gears driving the fast drum shafts. These are driven by worm gears on 3 horizontal shafts which run the whole width of the machine. You can see the so-called carry bars which move from side to side, stepping the ratchets which drive the slower shafts. There is a comprehensive one-shot lubrication system based on the Calumet vehicle lubrication system. You will see this as the network of small brass tubes and fittings running across the machine just above the horizontal shafts. On the electrical side, the machine operates from 200 volts DC and draws about 10 amps. It involves over 12 miles of wiring and many relays, both standard and high speed, and many wire-wound resistors, capacitors, though they were known as condensers in those days, and rectifiers. The next few slides were taken during the progress of the rebuild and should give an idea of the magnitude of the task. This is back in April 2002. The machine's main steel frame is complete, and the bearing plates, 1 pair for each Enigma, are in position. The task in hand is the addition of the drum shafts. You can see a few of these are equipped in the foreground. You will notice 1 long shaft fitted high up on the machine. This is actually the bearing alignment tool. The shaft fitting was a somewhat brutal process, with this tool pulled in the appropriate direction to flex the front bearing plate to permit the tool to enter the rear bearing. This is at the same stage, but viewed from the rear. Note the main drive motor at the bottom of the picture. This is a couple of weeks later. Bearing alignment and shaft insertion have progressed well and are nearing completion. Meanwhile, adjustment of the manual drive shaft bearing is taking place under the watchful eye of John Harper. Note the clutch assembly and gearbox driven from the motor belt and driving the vertical shaft, which in its turn drives the horizontal shafts. Here, horizontal shaft fitting is in progress. And in this rear view, you have a closer view of the carry bars that operate the ratchets of the slower drum shafts. The upper bar moves roughly once a second, and the lower one roughly once every half minute. Moving on now to mid-2004. Most of the wiring is now in place, but the machine lacks its covers and most of the relays. There is as yet no lubrication system. Here are the first few drums off our little production line. There are around 200 of these to be made, and we are currently, in 2007, around the 120 mark. All the other manufacturing is now pretty much complete. A little later, this time in October 2004. Although unpainted, the machine now has its covers, but still no lubrication system and few relays. This slide shows the back of the machine with its gate closed and the covers in place. This is very much as it would have appeared in service, though the finish would be black crackle paint. And now another couple of views from the front. Now we are moving up to date. Here in the first decade of the new millennium, members of the team are using 1980s test gear, an oscilloscope and a logic analyzer, to commission 1940s relay logic. The toasting fork with which I am being threatened here is actually a special tool for adjusting the machine's timing cams. And here we have project leader John Harper on the left with two of the commissioning team. This was the day when we got our first dynamic stop to work. We hope to have the machine fully operational by late summer 2007. During the war, the bombs were operated by women from the Women's Royal Naval Service, popularly known as Wrens. Here, one of the Bletchley Park staff is masquerading as a Wren for my final picture. For those of you still awake, many thanks for listening. Originally made in 3D, this film was played on demand in a small 3D theatre adjacent to the bomb rebuild. In the 9 years of the theatre's operation, it is estimated that it was viewed by some 180,000 members of the public. Now, in 2020, we look back on 13 years of progress since that earlier film was made. In mid-July 2007, His Royal Highness the Duke of Kent officially switched on the machine. From that date, the machine has been demonstrated to the public, infrequently at first, but with regular Sunday demonstrations starting in 2010 and ramping up over the subsequent 3 years to a full 7 days a week. This has been achieved with the help of a highly dedicated and efficient demonstration team trained and led by Tony Jarvis. The rebuild has performed as reliably as its wartime counterparts. Despite some problems, the machine has been available to support demonstrations on a daily basis with very few interruptions. The problems encountered have included a seized bearing, traced to a lubrication problem and fixed, also an incorrectly rated mains fuse. In recent times, problems of wear have arisen and parts replaced much as they would have been during the war. Cam followers and pawls were the parts affected. Problems encountered by the demonstrators are recorded in the logbook, and these are addressed by the Monday maintenance team, which also undertakes a programme of routine maintenance. There have been a number of so-called challenges with other organisations, chiefly GCHQ. These have all involved the other organisation sending out a message which includes a crib, in other words a section where we know the plain text. The message is intercepted. The challenge for the bomb team is to find the Enigma settings of the day. This involves deriving a menu from the crib, plugging this up on the bomb, running it, and recording and checking the stops. And with a valid stop, going through the process of extracting the steckerboard settings, then using clonking to get the Enigma ring settings. So far, finding the key of the day has always been achieved, usually taking less than 4 hours, comparable to the wartime achievement rate. After this, we are able to use our own Enigma or Typex to receive and decrypt the encrypted messages and to send an encrypted reply. Following the official switch on by the Duke of Kent, there have been other royal visits. Their Royal Highnesses the Prince of Wales and the Duchess of Cornwall visited in July 2007. Her Majesty the Queen and Prince Philip visited the bomb in July 2011. Other distinguished visitors have included Oliver and Sheila Lorne. These two distinguished wartime veterans were treated to a full demonstration in April 2007. Wartime veteran Marjorie Pattle visited in March 2008 and explained and demonstrated how she carried out clonking, which is the final step in getting the key of the day, during World War II. Stephen Fry visited in May 2008. Wartime veterans Mavis and Keith Beatty visited, and they brought along American computer scientist Frances Elizabeth Fran Allen. Fiona Bruce with the Antiques Roadshow team visited in July 2009, as did Dr. Tilly Blythe of the Science Museum. Sir Maurice Wilkes, designer of EDSAC, visited in the November. James May visited the bomb in March 2012, and Brian Cox and Richard Dawkins visited in August. Dan Snow visited in November 2016, and his quote was, "One of the greatest bits of UK engineering in history." Several awards have been made and accepted by John Harper, always on behalf of the team. Honorary Fellowship of the British Computer Society in April 2008. The Engineering Heritage Award from the Institution of Mechanical Engineers in March 2009. This is a great honour, ranking the project with the likes of Concorde. John was awarded an Open University honorary degree, Doctor of the University. A number of additional engineering projects have been undertaken. Modification of a British Typex encrypting machine to emulate Enigma. This involved making plugboard and reflector panels from original BTM drawings and making wheel internals to match the Enigma wiring. This was used regularly during challenges for deciphering and printing received messages. The pre-production 4 Enigma bomb prototype unit was developed into a useful display in its own right, adding diagonal board, lamps and a modern microprocessor control unit. This is called Petard. A set of German surface fleet additional drums was made. These are the cobalt, jet and silver coloured ones. This has enabled tackling the Scharnhorst intercepts. A working dummy checking machine has been built, and this has been made to look correct externally but internally uses modern electronics. It's a very useful piece of kit for training and for challenges, and was loaned to the Heinz Nixdorf Museum in Paderborn for a period. A 4th diagonal board was made in 2008 to model consecutive Stecker knockout, an exploitation of a German rule that a letter must not be steckered to an adjacent letter. This enabled the bomb to ignore stops which included a consecutive stecker. After the discovery and identification of a special slide rule in the museum at GCHQ, which enabled the transformations required in the process of clonking, a set of slide rules was constructed and are used by the team members during challenges. Working with Philip Marks, a colleague in the United States, We created a new reflector patch panel to emulate the Uncle Dick or Umkehrwalzer D. This enabled using the bomb to find the settings for a genuine wartime Uncle Dick message. In July 2014, the Turing Welchman Bombe Rebuild Trust was formed to handle the administration of the bomb rebuild. The trustees are mainly from the core technical and demonstration teams, plus one representative from the British Computer Society. In 2018, in the face of an increasing divergence between the approach to demonstration required by the Bletchley Park Trust and the aspirations of the Turing Welchman Bombe Rebuild Trust, it was agreed to move the bomb rebuild to the National Museum of Computing, the machine to be accommodated in a new bomb gallery adjacent to that which houses Colossus and Heath Robinson. This would create a new core of live code-breaking equipment within TNMOC. The move was funded by a most generously supported crowdfunding operation, and the move was successfully completed in April 2018. The bomb rebuild is now well established in its new gallery, the demonstration team is again fully up to speed, and one further challenge, with the Technical Institute in Poznan, Poland, during the IFIP World Computer Congress WCC 2018, successfully completed. On March the 14th, 2020, we celebrated the 80th anniversary of the delivery of the first bomb to Bletchley Park. This event included addresses by two of the world's leading experts on Enigma codebreaking, Dr. Marek Grajek from Poland and Sir Dermot Turing from the UK. Looking forward into the future, it is hoped that the Turing Welchman Bombe rebuild will continue to be demonstrated to the public in its new gallery in TNMOC for many years to come.